Welcome everyone to a brand new episode of Embedded in a Nutshell. Today we'll take a closer look at pulse width modulation, or short PWM. After this short tutorial, you will be able to use PWM to rotate the servo motor or change the brightness of an LED, either using bit banging or timers. Or you can also parse a digital value from a PWM signal. PWM is actually used quite a lot in our surroundings. It's used to dim LED lights, from commercial light bulbs all the way to the backlight in televisions. It's also used to control the speed of DC motors or to control digital RC servos in small toy cars. Furthermore, some sensor modules also have simple PWM outputs to read out the data. So let's dive right in. What is PWM? PWM typically refers to a signal with a specific shape. And this shape is fully described by only two parameters: the PWM frequency in Hertz and the duty cycle in percent. Here you can see a simple clock-like signal, which also represents a valid PWM signal. The frequency of this signal, and let's directly call it the PWM frequency, is 500 Hz. So one period, which is the time between two rising or falling edges, is 1/500 Hz or 2 milliseconds. The ratio of the time the signal is high and the period is called the duty cycle. Since it is 1 millisecond high and 1 millisecond low, we have a duty cycle of 50%. A duty cycle of 25% is 0.5 milliseconds high and 1.5 milliseconds low. 75% duty cycle is, you guessed it, 1.5 milliseconds high and 0.5 milliseconds low. Pretty straightforward, right? Let's now actually generate a PWM signal to control this servo here, using this potentiometer. Both are connected to this Arduino board here. We could now use the Arduino servo library to do so, but let's start with bit banging a PWM signal. Therefore, we configure a pin as an output pin and pull it high for a certain portion of the period and low for the other. And we determine this portion by the voltage level measured on the analog input. That's all there is. Let's upload it, and you can now see the PWM signal on the oscilloscope here. If I now turn the putty, the duty cycle changes and also the servo changes its position. So far so good. But the downside of bit banging is that the microcontroller is busy, either because of such a delay call here or because we constantly need to check if it's time to change the signal. There's actually a more clever way to set up PWM, and this is using internal hardware timers. These timers do not require software to work. They just need to be configured once and output the desired functionality, like a PWM in the background. Of course, if you want to change the duty cycle of the PWM, you need to change a certain register value. But that's it, no more bit banging. If you want more information about timers, check out our video on hardware timers. Instead of this servo here, we could also connect an LED to this pin. If we now rotate the potentiometer, we can see that the LED dims down and up depending on the duty cycle of the PWM. If we add a hardware low-pass filter, so just an RC circuit here, the digital value can also be transferred into an analog value. That's pretty sweet and does not even require a dedicated digital to analog converter. So after changing the code to timers, we are free to do something else with the microcontroller. What can we do? Well, let's actually read a PWM value which comes from another module. This RC receiver here, which receives inputs from an RC remote, outputs a PWM-like signal. It actually outputs a high pulse of 1 to 2 milliseconds, each 20 milliseconds, so around 50 Hz. And the length of the pulse holds the information. How do we know? Well, they are typically used to control servos in RC planes, which then move flaps or ailerons of them. To read these values, we can poll all the time. We could use the Arduino built-in pulse-in function, but we can also use interrupts. So let's do that. Therefore, we connect the output pin to an interrupt-capable pin of the Arduino. This Uno here has two of those pins, pin 2 and pin 3. We connect it to pin 2. In Arduino, we configure the interrupts so that a separate function is called whenever the value of the pin changes. In this function, we check the current state of the pin. If it's high, the change was a rising edge, and if it was low, it was a falling edge. To now read the pulse length, we measure the time from the last falling edge to the rising edge. We can do so by using the Arduino's micros function, which returns the current system time in microseconds. Subtracting the system times reveals the pulse length. As I've told you, the value is typically between 1000 and 2000 microseconds. So 1500 is the typical idle value. To now convert this into a steering value between -1 and 1, we subtract 1500 and divide it by 500. A little bit of clipping and we are done. We can of course do all these calculations in this interrupt here, but it's typically not a great idea because interrupts should be designed as small and as fast as possible. And using floating point arithmetic should be avoided. So we simply set a flag here in the interrupt when new values are ready to be processed and process them in the loop function. We therefore shortly disable all interrupts so that we can safely copy the current values into a new variable and afterwards re-enable interrupts again. Otherwise, the program could be interrupted directly at the point where we process the calculation and mess with the result. Perfect, let's add a little code to print out these values and let's take a look. As we move the stick of the RC remote, you can see that the pulse length changes between 1000 and 2000 microseconds. With something like this, we can actually use it to steer such a robot here, which motors are also controlled by PWM. With this fun little demo, let's summarize what we've learned. PWM can be used to control, for example, RC servos, but also to dim LEDs. If we add a low-pass filter to the output, we could even use it to output an analog value without a dedicated DAC. PWM is fully described by the two parameters, PWM frequency and the duty cycle. And microcontrollers typically have built-in timers which can help to output such a PWM signal. That's it for this short PWM tutorial. If you have further questions, write them down in the comment section below. If you like this tutorial, give it a brief thumbs up, and if you don't want to miss out on upcoming ones, subscribe to the channel and ring the bell.